Right. Hi, everyone. I'm Faez Ahmed. I'm going to talk about design and AI. And I want to start my talk with just an introduction. So I lead the Decode Lab, which works at the intersection of AI and engineering design. And a big focus for our group is thinking about how can we enable humans to create better designs faster. Today, I want to think a bit broadly about where our field is, and in some directions where our field is going, to kind of align with objectives of the workshop, is to identify, articulate, and advance research priorities and methods in AI at sea. So thinking about AI and at sea, I kind of took a step back, and I was glad to see that Harrison was talking a lot about 2008. So interestingly, I took a step back in history around 2008 when I was in India at IIT Kanpur, and I was building these robots. And I was working at this intersection of these three topics, robotics, AI, and product design. And Boeing was funding this work around like building these autonomous vehicles, which can go from point A to point B. And our goal was to come up with the design for these robots. Now, since 2008, a lot has changed. I want to look at a few things that have changed. So one is, if you look at a big motivation, this was a movie that came out in 2008.
Connect to the Cisco, have it reconfigure the shell metals, use the gold titanium alloy from the Seraphim tactical satellite. That should ensure fuselage integrity while maintaining power to weight ratio. Got it?
Yes. Shall I render using proposed specifications?
Roll me.
So what we are seeing here is Tony Stark from Iron Man in a movie that came out in 2008 is talking to Jarvis, his AI, and he's designing his Iron Man suit in a way where Jarvis understands his requirements and comes up with new materials, new systems to design the whole thing. Now, how has the field changed? Let's look at where robotics was in 2008. So this is the robo competition in 2008. And you can see where the best robots were. Compared to now, if we look at 2025, some of the robots that are there today, we see that a lot has changed between 2008 and 2025. Right? In the 17 years in robotics, we can see a huge difference. Similarly, if I take a step back and talk about AI, this is Jan LeCun, who is talking about his CVPR paper. And basically, he's holding his camera and trying to show that his model can tell whether this is an airplane or not an airplane. The model makes some mistakes. It like comes up with some objects which are not there. But overall, that was the state of AI in 2008. Compared to, if we look at some of the recent models, I think a lot of us know about different parts of AI from ChatGPT and so on. This is just one example of DeepMind, where it's creating entire live environments, 3D environments on the go. So this is for gaming environments, but it's creating 3D assets. It has some understanding of physics, and it does a decent job of creating things as we are moving around. Right. Now, I also want to take a step back and think about where robot design was. So this is me giving a talk in 2008 to Boeing representatives and talking about my frustration of designing these robots. And I say like, oh, this was, we designed one robot that had some issues, that we wanted to improve the aesthetics. There was like bending issues, and we came up with design back and forth. And I remember this was like really frustrating back then because we had to do this CAD, and then we have to prototype it, and so on. And when I look at our MIT students here, interestingly, our MIT students are also using a very similar process. They are saying it is more complicated than it has to be, but it's more about like you basically have to go ahead and prototype things, and you have to go back and forth through this process of designing the product, use similar CAD software as I was using. And there is still a lot of room for improvement. Now, of course, like this is anecdotal. And also, this is limited to college settings where people have limited resources. So I wanted to think broadly about design. And again, design could be a lot of different areas, from wind turbines, nuclear, to car design. And I picked car as one specific example. In 2007, there was this report from automakers where they were talking about how the time it takes to build a new car is one of the biggest problems, and it takes them 2 to 3 years. And this is one thing they want to improve. So they want to improve like going from an early concept to a car in the market. And this is from 2025 summer this year, where Nissan CEO was said, we are too slow. This is one of the things we have to face. And there is at least $1 billion between now and 2028 that they can save if they can get down the car production time from 50 months to 36 months. So again, we are making better cars. We have improved a lot in terms of the quality of the car, but this is still very hard problem to solve. And again, some of the reports are also talking about how AI and automation can help with this. But I want to just highlight that inherently, this is a hard problem to solve. I mean, if we just think about the car design process, anyone who has worked in the car industry, they would call this middle part as the devil's cycle, because the CAD guy sends their CAD model to the simulation person, and they have to go back and forth between actually making the changes in the CAD and the simulations, and the early stage concept designer doesn't have a very good idea of what's going to happen downstream. Because of this, there's time and efficiency loss, there's lack of innovation, and also there's difficulty meeting requirements. People take last year's product, tweak it a little bit, and come up with the next year's product. So while we have made substantial progress in improving parts of this design progress, of the design process, there are still many, many challenges remain. And one of the goals of this workshop is to think about how can AI potentially help with it. AI is not the only solution. There is lots and lots of other factors that come into play, and it's an inherently hard problem to solve. So just to kind of talk about AI, the lighting is not great here, I think. So thinking about AI, I think AI moves around a lot of sectors, from transportation, agriculture, to manufacturing. And someone may ask, why do we want to consider AI? And there are a lot of factors that goes from different sectors. But one of the key things that I think about is basically we are thinking of some form of, some way of creating better products, and we want to do it faster, right? And better could be higher quality, it could be more sustainable, it could be many other things. We might also care about other factors like unlocking new design capabilities, innovation at scale, and democratizing design. And we are already doing a lot of it. If you look at our papers that are coming out and research that is happening, a lot of research around using AI for engineering design to inspire and ideate, to create new concepts, to evaluate designs, creating surrogates, simulators, and so on. We are also looking at a lot of optimization methods, decision-making criteria, modeling and analysis, generative models, and so on, right? So I wanted to be a bit more quantified in understanding what is EDSE and what are people doing in AI for EDSE. To do this, what I did was we collected all the papers that have ever been published in JMD and JSICE as two representative journals. Again, this is not our entire field, but this is our representation. So what you're seeing here is every dot on this graph is one of the papers written since 1978 to today in JMD and JSICE. And we have projected, using dimensionality reduction methods, we have projected that on a 2D map. So what we start seeing is, like if I hover around, you'll see like some papers are around some topics. The more red you are, that means those are more recent papers. The more blue color is on this side, you can see that you have more older papers, right? So JMD started around 1978, JSICE around 2001, and so on. All right, so given this data, we can see how the field has evolved. So these are papers coming out across time. And I can start already seeing that if I look at every 5 years, like our field has been pushing into newer and newer groups of papers that are coming out, and that looks interesting. We can also see, like, we can start exploring the space, so we can start moving around our mouse and just trying to see what papers, and I think just by design space exploration, you start to see that this whole area is about gears and kinematics and so on. Like there is more machine learning and design theory and design education that starts coming out in the field, right? In general, there is a trend within machine learning that we see knowledge-based engineering moved on to optimization surrogates and then to deep generative methods. So we can come up with different groups of papers that are coming out. Again, I've just noted a few of the groups that are coming out. And we can also, I'm not sure if it is very clear from the back, but you can see if I look at the centroid of all papers that were published every 5 years, there is a trajectory where it slowly moves towards optimization and machine learning compared to talking about gears and so on. So every 5 years, if you look at all the papers and find what was the centroid of those papers, we are seeing a slight shift. The centroid was closer to flexures around 1980. Around 1990, the centroid was closer to manipulators. Then around 2000, it was closer to topology optimization. Around 2015, and 2010 to 2015, it didn't change a lot, but it was mostly around surrogate models. And finally, right now, it's closer to machine learning for topology optimization. Again, centroid is not very representative because maybe the field is growing, the centroid stays same. So what we did was we started looking at just using keyword searches, collecting a lot of keywords, and trying to see how have the papers mentioned in their abstract, title and abstract. And this is, again, a surrogate, so it's not very accurate, but it gives us an idea. How have people been mentioning these terms in their papers and abstracts? And a lot of different terms related to machine learning, so I came up with a list. And interestingly, there was a very nice trend. If you look at 1978, and this is only JMD because mixing two journals can get confusing. So we see there is an increase in machine learning over time. Around 2008, we see a sharp increase. It was around 10% in 2005, 20% in 2013. And also, the biggest jump was the year of ChatGPT, where we saw about 11% increase in machine learning and AI being mentioned in the papers. And it's not just that. We are also seeing some very interesting trends. And I mean, you can spend 6 months just understanding all the data. But the key thing is that now we are seeing that the Shannon entropy is highest around AI/ML portfolio. That means that recently people are working on not just one or two methods. There's a lot more methods people are working on. There's no kind of single one or two dominant methods. We are also seeing that the variety of technical terms has grown. So basically, people are also talking about more and more new terms that were not there before. And we are also seeing a lot of hybrid modeling, which means that people are not just doing deep learning. They're combining terms like deep learning and UQ or deep learning and GP surrogates. So there is a lot more that is happening in the field around kind of mixed methods, which is all quite interesting. And we are seeing a big increase in these topics. And it's not just research. If I kind of look at only this summer, I was just quickly looking at 4 companies which combined raised to more than $200 million this summer to work on AI and machine learning, which includes like P1 AI Foundation, this neural concept, and PhysicsX. These companies are already kind of new startups are now beginning to work on these topics to kind of push problems at different frontiers. And also on the right side, there are a lot of companies that I directly work with, and these companies also have dedicated teams which are working around this topic of AI and EDC, thinking about different problems of the process. So we are seeing a kind of a big increase in AI and EDC. And one of the questions that comes up is, what are the key challenges? Now, thinking about key challenges, first I wanted to look at an insider perspective, which is people who are in the community and how are we thinking about it from a research perspective. For this, so Mark, Wayne Chen, and we recently were writing a perspective paper, and we tried to think about how can we divide the problems across different axes. And one of the things we did was we identified 2 main axes. One was, what are the scientific challenges? And one is, what are the deployment challenges? So the science exists, it's just about deployment. The other axis is design depth versus design breadth. In some cases, we might want to actually improve on very, very specific cases of one step of the design process. And sometimes we might actually want to go across the design process and think about the breadth of the design process and how do we improve on those. And for each of these quadrants, we can start thinking about what are the challenges with respect to each of these quadrants. And those challenges could be around data and infrastructure. There could be model capabilities not there, generalization, workforce and organizations, and trust and compliance. There are lots of other factors. Again, I'm not an expert in workforce and organization, so I'll mostly talk about the first 2, which is data and model capability. And within that data and model capability, I think these are some of the factors that I've been excited about recently, just thinking about how the field is, what are the key challenges in some of the AI and machine learning methods, ranging from lack of data, representations, dimensionality, and so on. So let me just state a few of those challenges. One of the first challenges is representation. Like when we think about design, how do you actually represent a design in a computational format that can be used by AI? And it's generally one of the biggest issues when we are thinking about design as a field, because there is no single representation that works for everything. Like it's not just text, it's not just images, right? And just to give you an example, if I only pick CAD as an example, or 3D objects, one can represent a 3D object as a mesh. You can represent it as a feature tree. It's a program. You can represent it as a video of someone using a CAD software. You can represent it as point clouds. You can use implicit functions for 3D objects. And currently, if you look at the landscape of AI and machine learning, while multimodal models are coming out, they are still in their infancy. There is a lot that can be done to improve those models to work across these modalities. And this is one area which will directly impact both depth and breadth. There is also a big issue around a lack of data sets. So we had recently a JMD special issue, and we got a lot of great contributions around data sets for design. Having said that, if we look at our field, like we are mostly restricted to very small data sets, while if we look at modern AI, generally there is like huge data sets from 10 terabytes to 10 billion to 10 trillion tokens, while we are mostly limited to, like we are lucky if we get 100,000 items. So now we have to either create more data sets or come up with methods to live with small data sets. And talking about creating more data sets, this is just one work that, that my group did last year, where we created a data set called DriveAirNet++. And I'm using this as an example because it highlights one of the key issues of creating engineering data sets. So we spent about 3 million CPU hours. This was one of the largest simulations that was run on MIT SuperCloud. And it took us 39 terabytes of storage to actually create a data set of 8,000 cars with their simulations. And it's really important because this data set has been very popular since we released it. But if you look at modern AI, some of the largest large language models, they are trained on 1.5 trillion to 15 trillion tokens. That basically boils down to about 6 to 60 terabytes of space. So it's not a lot of storage when you think about it. While our data set, only a single boundary condition is taking 39 terabytes. If I go ahead and start changing, I mean, we are basically talking about data which is at a much larger scale than modern AI. That when we are talking, and that comes with how do we actually pay for it? Who creates those simulations? Who does the simulations? Where do we store? How do people train on these models? And unlike modern AI, where there is like big tech involved heavily, we don't have that much compute as a field. Also, like some people may say, okay, maybe we don't need large data sets. And I would argue that in general, scale and quality of data set matters a lot. So here is just one example of some of the data sets for car design. And you see DriveAirNet++ is sitting on that corner, which is 8,000 cars. And on y-axis is your diversity. The bigger the circle is the fidelity of the simulations. If I train only on the existing data sets before DriveAirNet, I would be limited to a very small design space. So the gray and the blue are previous data sets. So models trained on that will work well on that data set, but it will not generalize. On the right side, you see if I have more and more data, my loss function keeps going down. So that means if I had stopped halfway and said, I only need 4,000 cars, then I would have actually had a machine learning model which was performing much worse than if I had trained on a lot more data sets, a lot more cars. So there is, in general, the scale is something where we can see that machine learning models benefit from scale, but scale is hard for our field. And also, like, we have to think about the quality of the data sets. One of the reasons that this data set got a lot of interest from all these tech giants, automotive sector, and simulation software is because they found that the data set was closer to the quality that they saw in the real world. Like they are actually using these surrogates for designing cars. And this is one thing where we have to find ways to bridge the gap between academia and industry and come up with machine learning models and data sets that work in practice. All right, related to that is also this idea of benchmarks. So this is ArcAGI, and on the right-hand side, these are two benchmarks in computer science. And when a new model comes, when OpenAI announces, I come up with this GPT-5, a lot of times, like within a few days, you can go ahead and look at this ArcAGI leaderboard and see how close is it to like the grand prize or the human performance. And with this, all these companies which are coming up in computer science across different models, they can see the progression of their own field on a standardized benchmark. Now, benchmarks are interesting because if you look at the field, you need a lot of benchmarks because each benchmark it's like an exam. It's representing a very narrow view of a particular skill set. But not having benchmarks is also a problem because then it's difficult to know when is real progress happening across different fields. So I'm glad to see that there is a lot of work happening in this area. So my group has worked on bike bench and car bench, and Mark recently created NG bench, which is like bringing in a lot of data sets and problems, and now people can go ahead and create these models which work across different problems and not just for one problem. And it's easier to actually compare apples with apples and in a very standardized setting. And this is important. I mean, we have actually been working with many car companies, and we see, like, for example, if ANSYS or Beyond Math or some of these other companies come up with a new model, how do we know if it's actually a better model? And one thing we have been doing is really benchmarking. And for example, like Transsolver is an open source model that is out there, and you can see that even right now, it's on the Pareto front. So there's all these companies who are coming up with models, or all these groups which are publishing models. But it may or may not be actually outperforming unless we compare apples with apples and think about where is real progress happening on a standardized problem. Having said that, too much fixation on benchmarks can also be counterproductive. However, right now as a field, we have very few. So having none is worse than fixation on benchmarks. Now, finally, I also want to think a bit about one change that has happened over the last few years, which is a shift towards foundation models. And when we think about foundation models, a lot of us are thinking about ChatGPT, Gemini, Llama, Claude. But foundation models are much bigger than that. If you look at Stanford's definition, they talk about a foundation model is incomplete, but serves as a common basis from which many task-specific models are built. And one example is here, where you have a foundation model, and you can look at the grounding dyno, which detects everything, and then you have another foundation model that builds on the previous one to detect and segment everything. So thinking about what are those foundation models for engineering, where one model trained on one task can be used by a lot of other foundation models, which can not just do one thing that they are trained on, but many other things. And this is one area that personally I'm very excited about the future, because some of the early results seem to be pointing to some promising ways. And here is just one example. Like last year, we published a work at JMD where we were looking at this tabular foundation model. And again, this is not ChatGPT and LLM. This is a model which works with numbers. And we saw that this model was trained on completely synthetic data, had never seen any engineering data at all, by creating these graphs and trying to predict these values. And it outperformed all the models that were trained on engineering data. And this is really important because a model had only seen completely synthetic values, and it works better both with respect to classification performance and with time. It was faster and better for a lot of engineering problems, for airfoils, bicycles, solar hex design, truss design, welded beams. And it also works out of the box. So if I give you my model, you don't have to spend a few days tuning the parameters and being an expert in a specific area, or in some cases doing a 5-year PhD to actually just make one model work for one problem. You can just apply it out of the box, and it works better than many of the like domain-specific models. And this, to me, is, I think, quite promising, because we applied it for Bayesian optimization, and we saw that we can do significantly better. And not just for one problem, we can do it better for a lot of engineering problems. And we can also enable new capabilities, like working in Bayesian optimization up to 500 dimensions. So thinking about how can we create foundation models and how can we use foundation models could be something that is very interesting for the field. And on that note, I think one of the key things that something to think about is this idea, this article which was written in 2019 by Rich Sutton, which talks about the bitter lesson. And in this article, Rich Sutton talks and says that the biggest lesson that can be read from 70 years of AI research is that general methods that leverage computation are ultimately the most effective and by a large margin. So what he's basically saying is, if we handcraft our strategies, we get big gains in the short term. And it's actually quite attractive to do that, because we show we are the experts. We come up with a very nice handcrafted way to make a model work. But over time, we underestimate how fast compute is growing, how fast overall storage is growing. And what we see is that across fields like chess, computer vision, speech, coding, protein folding, the general models have always won across compared to the domain-specific models. So one of the things that we may want to think about is, what are those general models for our field that benefit from compute and data? So right now, we have a lot of interesting new ideas that are coming up, but we still are not very close to the ChatGPT moment for our field. So the other perspective I want to present is an outsider perspective. And this interestingly came up this summer, where a DARPA program manager, a couple of DARPA program managers approached me, and they started, they had looked at some of our works, and they said, what can we do to enable the ChatGPT moment for engineering? And in this case, what they were interested in is creating a DARPA challenge. So people who, around 2004, 2005, we had this DARPA Grand Challenge where they asked to drive a car autonomously across the desert. And first year, it was a big failure because no car actually got out of the gate. And then second year, it was a big win. And that was the start of this whole autonomous vehicle revolution that became very publicized. In fact, the project I was working on in India back then was inspired by this DARPA Grand Challenge. So it was like a full circle for me. And for DARPA, thinking about how can they change AI for design by huge investments is also interesting, because they are thinking on how can we get rapid on-demand design and field new systems. Because if you are in the field, you might have big changes. They're also interested in revolutionizing commercial product, democratizing design, and fostering open innovation. So we spent a lot of time. We had we had a full day workshop. A lot of people came in to give ideas. A lot of outside people came in. And one of the key things that I already identified was also identified from this outside perspective was that the single greatest barrier to achieving a ChatGPT moment for engineering is acute scarcity of data. And it's also a market failure because most companies are not incentivized to kind of share their data. A lot of the data sets are suboptimal designs. They are not real-world designs. And most of the data sets are missing tacit knowledge. It's not really capturing how engineers think about a particular field. So this was one of the issues that was identified. We also identified some AI cognitive deficiencies. So what is the deficiencies that current AI can't solve? So it's not just that we can use it, because current AI can't even solve it. So one is the reality gap. The AI does not match the reality. It is kind of limited. There is also the spatial reasoning gap. And this is one example. In 2023, some of my students were working on how can we test AI's capability, like foundation model capability, in just basic spatial reasoning tasks. And it failed miserably. It was near random choice. So it was picking randomly. In 2025, we again checked it. And we found that some of the best models, after thinking about 13 minutes, still struggle with spatial reasoning. So there is not a lot of improvement that we are seeing around things like spatial reasoning, precision, and physical intuition. Also, there were issues around engineering process and ecosystem gaps that were identified. For example, there is a lot of problems of fragmentation and non-interoperable tools. Limited scope, like most of our AI models are limited to single components and not entire systems. And systems are very more interesting, and in real world, you rarely have individual components. Lack of APIs with suppliers. How do we actually connect it with the suppliers and the products that are out there? Slowness of hardware innovation, adoption risk, and inertia. Need for open standards. So a lot of the, I think when we look at fields like CAD and simulations, you're mostly tied to specific formats and specific ways in which these models are built, and also IP restrictions. And just to look at CAD, you can see a lot of these CAD softwares, in additive manufacturing. These are all the companies that are working, they have softwares around this space, around design and printing. And you can see that there is just this huge plethora of methods of software which are restricting AI to actually be able to learn in an open way. We are also, I think, thinking broadly. I think right now this is still ongoing. There's a lot of discussions going on. I would love to have your input around this, thinking about like what is the data that EDSE needs. So one of the questions that was brought up was like, if I spend $50 million and you are my customer, what is the data that your field needs that I can basically get that data for you? And to us, like, I think that's a really important question, is like, if some magical thing happens and someone wants to give us the data somehow, what do we need to actually change the field? And what are the key real-world problems? Like, for example, in DeepMind created the AlphaFold, and that really enabled a lot of new things. What is the key problem that we can see? Is it like going design, build, and fly, like this AI AA challenge is showing, where we say, you know what, we want the AI to actually come up with an aircraft and build it and fly it? Is that the problem that we are looking for, or is it something else? So it's still a lot of things to think about, and this is not just specific to DARPA. I think it is like this may or may not happen. It's still early stages, but I do think that these are some of the topics that were interesting to me from an outsider's perspective, and I thought we should discuss this in the community to see how others are seeing our field. All right, so what's next? First, I want to highlight that physical AI is hard. Here you see like one of the best video generation models trying to create a car crashing into a balloon, and there is almost everything that is wrong with it in terms of physics. And we have to see that current AI models there is still huge room for improvement, both from a methods perspective and usage perspective. Having said that, there is promise. So if I look at large language models, they are doubling in every 7 months in the complexity of problems that they can solve. So we have this graph of time. And again, this is a surrogate of complexity, but we are seeing that there is big improvements in how complex the task the models can do. So imagine extrapolating these trends and what will happen in a decade when these models get better and better, and we are part of actually making them better. We are also seeing more and more research. So this is like a number of papers that have been published around AI. So there's a lot of people who are thinking about this topic, and it's an exponential increase, almost linear in log scale. We are also seeing the cost of AI is coming down. So there is, last 2 years, there has been a 99.7% drop in the cost of AI. So what this means is what seems quite expensive today, if this trend continues, we might actually have models which are much more affordable in a few years. And finally, we are in 2025 right now. This is where we sit in terms of the GPU compute that are there. And if you look at the current projections of how many GPUs we'll have in 2034, in about 10 years from now, both in North America and across different countries, it is quite likely that we'll have a lot more GPU than we have today. And this would enable us to kind of start solving much more complex problems that are possible. So with that, the hope is that we can start thinking about how we can create better designs faster, accelerate scientific discovery, and enable design democratization. And I want to highlight the last point, because this is something that really excites me. When I go to ChatGPT, and this is like the first version, and I ask it to write a poem about kinematic design of linkage mechanisms, it writes this poem about robotic arms with joints so fine, move with grace in a straight line. Machine learning is the key, it seems, to design them with great esteem. By my standards of writing poem, and my wife can vouch for it, this is an amazing poem, right? I start thinking about also art. Like this is my 4-year-old back then. She created a doodle, and AI can take and hallucinate a lot of it, but it can create art like an artist would. And the question is, what can we do to help both novices and experts in understanding the requirements of a field and preferences, simulate, prototype, and produce manufacturable designs to create the next generation of flying cars? And not just about cars, but this applies to almost every product that we are surrounded by. And how can we really reduce the barriers of entry and tap into the creative potential of a lot of people? So that, to me, is very exciting. Again, my group works on some small aspects of this problem, thinking about generative models, multimodal learning. If you're interested, I would love to chat, and I'm also looking for a lot of great ideas coming out of this workshop. Thank you.